Hello guys, welcome back to the LearnRISC-V channel, and in this session I'm gonna discuss about the privilege level mode switch from machine to user mode in RISC-V. So these are the four privilege levels in RISC-V, and among these four, one is reserved, and among the remaining three, so the machine mode is the mode which is mandatory that every RISC-V core should support, whereas the user and supervisory mode, it's optional based on the need or use of the RISC-V core. So before we look into the privilege level mode switch from machine to user, it's important to know about a few control and status registers, and also you need to know how the control flows between the normal operation to a trap, and how these CSR registers play a role during this control transfer, and also how this might affect the privilege level mode in RISC-V. Okay, and whatever I discuss here, it's specific to RV32, and also as we go further, it might be specific, few things might be specific to FE310 SoC, which has the E31 core from Sci-Fi. Okay, so let's look into this slide. A lot of things have been packed in this one slide. So let's pretend that this is the current execution flow. So the program is being executed from 7 followed by 7 zeros in the RAM memory, and at this address a trap has occurred, and then the execution would jump into the trap handler, and let's assume that the trap handler is at 8 followed by 7 zeros of the RAM memory, and once the trap is handled, then the execution returns back to the normal operation. Okay, so these text are these are all CSRs which are highlighted in yellow within the square brackets. So XTVEC, XEPC, and XRED. So these are CSR registers, and this X, there is no CSR register named X. Instead, this X here you can replace with any of the privilege level like UTVEC or STVEC for supervisor, and MTVEC for machine mode trap vector. Same for SEPC for supervisor exception program counter, and MEPC for machine exception program counter. Similarly, you have three instructions: ureturn, uret, or mret, or sret. Okay, so how these what is the role of these CSRs? Or that, so when the trap occurs, the source address or the address at which the trap occurred is stored in the MEPC or SEPC register based on the current privilege level. Okay, and then the execution jumps into the trap handler, and once this is handled, when it returns back the address from the XEPC, in this case this is the next address following the trap, so this would be this address, and the execution jumps back to this and it continues. Okay, and in M status CSR register there are 2-bit fields which would record the previous privilege mode before it gets into the trap handling. So for each level there will be a status register. So this M status or the S status or the U status correspond to the status register of these three modes for a particular heart, and this is a register that will track as well as control the heart. Okay, so these are to say in simple text. So when trap occurs, execution jumps to the address mapped to the xt vector, so the M or S or U T vector, and then handle the trap and execute xret, the corresponding return instruction, and get back to the original execution flow. Okay, so just keep this in mind as you might need to know this before we get into the privilege level mode switch. So this is the M status register, and if you see here, as I said before, this is the register that keeps track of and controls the heart's current operating state, and this has field which is like MPP, which stands for machine previous privilege, and supervisor previous privilege, and machine interrupt enable or not, as well as a supervisor interrupt enable, so on. So these are all the main state variables for a particular heart, and this is the most important register. Okay, the CSR. And now let's see how the privilege level, how to switch from machine mode to user mode. So very first, before you right after the reset in the E31 core, the M status, the machine interrupt enable bit in the M status would be set to 0 at reset. That means that the machine interrupt is disabled, and then we have to map the trap handling address to the MTVEC. So these are all mandatory because the machine mode is the highest privilege level mode, and it should be able to handle all the critical traps. So this MTVEC has to be mapped to something, and then so this machine previous privilege bits in the M status is the one that controls which mode should this trap handler, when it returns from trap handler, which mode it should return in. So if the execution jumps inside the trap handler in machine mode, and if it has to return back in user mode, then you have to just set this machine previous privilege to user level, which is a 0, and then you need to configure physical memory protection. We will see this later. What is this all about? And also sometimes in some code you might have to delegate few of the exceptions. For example, if the user or supervisor mode, if few traps can be processed in non-machine mode, then few of those has to be delegated to the supervisor or user, but that is not applicable for E31. That also we will see why. And then the MEPC register, which is the program counter value to which the execution should return after executing this mret, that has to point to the user mode entry point, then execute the mret. Okay, and this would be more clear when we try on our card or the Hi-Fi 1 revision B board. Okay, so let's get into the code now. So this is just a very simple code to test this privilege level mode switch. So if you are following the Git repository, which I have been using for the LearnRISC-V channel, then in that I have created a new app, UM or user mode, user to machine mode switch, or UM-mode switch directory, and I have one assembly file. So right after the reset, this code would just set the stack pointer and map the empty vector or the machine trap vector, and then it would just jump into the app entry, which is this code. Okay, so let's read the values of this yum status right after the reset. So I hope you can see this terminal at the bottom. So this is the terminal where I run the OpenOCD, and here let me first build this. So these are the values of the yum status register right after reset. So if you see here, the machine previous privilege is 3. That means the machine previous privilege level has been set to machine again. Okay, and machine interrupt enable and supervisor interrupt enable, all those interrupts are disabled now. It's all set to 0. Okay, so let's step in. Oops, sorry, I think I did not load the code. Okay. So from the object dump of those ELF, you can see the machine trap vector is mapped to the trap base address. So this happens in this start entry function. Okay, you can see here, and then it should jump into the app entry. Let's step in further. So right now the execution is here. So what these 4 lines do here is I have created a mask for the 2 bits in the MPP, that's bits 11 and 12 in the M status register. If you see here, those 2 bits alone are set to 0. So I just read the M status value into T0 and with those two, so that the MPP bits would be set to 0, which correspond to user mode. Then I also enable the machine interrupt. This has no role now, but for now you can skip that, and then I write back into the M status with the MPP set as user mode. Okay, and then I load the address of the user entry point. So if you see here, this is the just a function named as the user entry point, and the address of this is loaded into the MEPC. So if you see here, load LEA means load address. It's a pseudo instruction right into the MEPC register, and these are the physical memory protection settings. So let's not get into this, but let's execute and see what happens. Okay, so right now it's here, and you see here, so the machine previous privilege has been set to 0. That means it's set to user mode. And now what I'm gonna do is I'm just gonna keep a breakpoint into the machine trap vector. So I'm gonna execute this. So let's read the MEPC register now. So after reset, it has some random value, but once we execute this line, let's see now. Okay, PC should have the, okay, so 570. So 570 correspond to the address of user mode code, okay, or the user entry point. So that has been loaded into the MEPC register, and then we do some physical memory protection settings. Then I have already kept a breakpoint in the machine trap, and let's execute, and you can see that some trap has occurred and it has hit the breakpoint. So if you want to know what is the cause of that, there is an cause register, what has caused this, and to get from where this trap has occurred, that is the MEPC register. Now let's see what they are. So for FE310, these are all the exceptions. So these are few. If the MSB bit is 1, that doesn't interrupt, whereas when the MSB bit is 0, and if the MCOS has these values 0, 1 or 2. So right now what we see here is that exception number 2, which stands for illegal instruction. Okay, And what is the line number or from where that has been caused is MEPC, the program counter, is this 8 followed by 40 and 584. So now from the object dump, let's go to the code, what that is, which is nothing but CSR write into MIE register. So if you go to the user mode code, and this is the line. So why this line in this function has caused a trappers? So as long as we were in the machine mode, it's allowed to write into any of the critical CSRs. So that's why we have been able to write into machine status and MEPC and so on. So, but after this execution would jump into the, so at the end, when the mret is executed, so the MEPC has the address of the user mode code, and it would jump here, and in the user mode writes into this critical CSRs are not allowed. That's why the trap has occurred. Okay, so that means that our code has successfully changed the mode from machine privilege level to the user mode. Okay, and now let's go to the spec CSRs. So when I talked about these CSRs, I mentioned that X can be U or S or M, any one of the privilege level. But what I see from the privilege spec, excuse me, is that, so this is a privilege spec from 2019, and if you see here, the user level or the user mode has UTVEC or user level trap vector, and also UEPC. And if you go down, same for supervisor level, STVEC and SEPC, and further down the machine mode, MEPC and MTVEC. But if you move on to the latest privilege spec from year 2021, I see that this is hypervisor. So you still see the STVEC and the SEPC for supervisor level, but the user level trap vector and UEPC has been removed. So that means that so after this spec, so there is no way that, or it's handling trap in the user mode, it's not supported anymore in the privilege spec. However, there is some details on the unprivileged spec on how to handle the user trap and so on. So okay, so just want to clear that there is no UTVEC from the latest spec from 2021. That's okay. And so the physical memory protection, why we have to take care of that is, so let's, for example, let's see what would happen if we comment these. Okay, let's comment these 5 lines. So if you see here, once you comment this physical memory protection configuration, then the cause of the trap now is instruction access fault. So the previous trap, when we switch from machine to user, and when we try to access or write into this CSR, it was throwing the illegal instruction, whereas now it clearly shows that there's an access fault. And to know what has caused this, if you just see the MEPC register, it would show the address of the user mode entry point, which is 570 here. So now why it throws an access fault is that by default, if you see there's a set of registers to configure the physical memory protection. I can just, so if EMP-CFG 0 and 1 and 2. So at reset, these has some values, but to enable these execution or to enable read, write, and execute a particular memory in the RAM or flash, then those memory locations has to be enabled in the PMP to be accessed in user mode. So I have planned to cover the physical memory protection in another separate video, because this session is for just discuss on how this mode switch happens, but I have this one slide. So you have the address and the config registers, like I was shown here. You also see PMP ADDR1. So each PMP configuration register is backed by an address register. So for a particular address, whether you want to give read or write or execute permission, so PMP is also part of the privileged spec, and it is also there in the E31. You can see the PMP specific to E31 and the E31 manual. Okay, so that's why we need this to enable the physical memory protection. That's what I have mentioned in the bullet point 4. Okay, so that's the end of that, and see you soon in the next session. Thank you.